As we learn about exponential applications, we're going to break these down into a series of different videos because there are actually a lot of applications for exponentials. We see them a bit more often than you would with polynomials in real life. So when we think about exponentials, we often see growth and decay. And we've talked about the general exponential rule before, and we always have a base to some exponent. So let's start with this scenario where we have a single bacteria cell that splits every hour. How many bacteria will there be in 3 hours, 7 hours, or T hours? So think about what we have. You have a single bacteria cell and it splits after 1 hour, making 2. And then after another hour, that one splits into 2. And then this one splits into 2 more, so there'd be 4. And then it just continues to keep replicating itself. So based off of that, this is at, let's say, 0 hours, 1 hour, and 2 hours later. So 3 hours, we would then have that one split, this one split, another split, and one more split. So after 3 hours, that would make 1, 2, 3, 4, 5, 6, 7, 8 total bacteria. Eight bacteria. All right, if we had 7 hours, if I continued that process, we'd want to think about how is that going to keep going and going and going? Well, maybe we make a table to make it a little bit easier. And I'm actually just going to redo this here. So at 0, there was 1 bacteria. After 1 hour, we then had 2. After 2 hours, we had 4. 3, we now had 8. After 4 hours, there's 16. After 5 hours, that 16 is going to double again to give us 32. After 6 hours, there would be 64. So after 7, if I double again, I get 128. So we can see after 7 hours, there's 128 bacteria. But what about T hours? Basically, so any number of hours. We want to create a rule for this. How could we find it? So what's happening each time is that we are multiplying by 2. So if I started at 1, I'm multiplying by 2, and then by 2 again, and then by 2 again, and we keep going. So repeated multiplication can be rewritten as 2 to some power. So I started with 1, and then we keep multiplying times 2 to some power. So for T hours later, I would say we just do 1 times 2 to the T power. Now, in the second part, we say a scientist collects a swab of bacteria onto a petri dish. Initially, there were 50 bacteria cells, and they're going to continue to split every hour. So instead of starting with 1 bacteria, we now have a collection of 50. At the very beginning. So 1 hour later, those 50 have each divided in half to make 100 bacteria cells. So after 2 hours, we're going to have 200 bacteria. So there's the first part of that. There'd be 200 bacteria. 5 hours later, well, we just keep going. So 3 is going to be at 400. 4 would be at 500, not 500, 800, sorry. And 5 would be at 1600. So what about T hours later? Well, if I just continue this process, the only thing that's changing is that we started with 50, and then we multiplied by 2 to get 100. Then we multiplied by 2 again to get 200, and we continued to multiply by 2. So that is what's creating our 2 to some power. So we would make this 50 times 2 to the t power. In this next one, the scientist collects a different strand of bacteria on a different petri dish, which initially has 10 bacteria cells. These bacteria grow slower and they split every 3 hours. So if we think about how much we started out with, at 0, there's 10 bacteria cells. But after 1 hour, how many would there be? Well, it splits every 3 hours. So they haven't fully split yet, so we don't know. At 2 hours, we don't really know. After 3 hours, they've now finally doubled and we'd have 20. So it's taking some extra time here. And at 4, we don't know. At 5, we don't know, but 6. Another 3 hours later, those have split again, so it'd be at 40. And we see something that's just slightly different than what we had before. So I started out with 10. It's still doubling, but it's not doubling every 1 hour. It's doubling every 3, which means it's being multiplied by 2 when I reach 3. So I need something to where I fix this exponent to be it's only multiplying by 2 one time after 3 hours. And then by 2, it's doubled twice, so 2 to the second power after 6 hours. So how can we get that t value to become a 1 at 3, a 2 at 6? We would divide. So I take that time and I'm dividing by 3, because 3 divided by 3 would be 1 time. 6 divided by 3 would be 2 times. If we continued on at 9, they would have doubled again to give me 80. So that would be the third time that they've doubled. 9 divided by 3 would be 3, so it's doubled 3 times. So our equation, our function rule, would say something like y equals 10 times 2 to the t over 3. This is beginning to show a foundation of what this exponential growth or decay function is. And so I had it up here at the beginning, but the a value we've seen is our initial starting amount. Sometimes you'll see that as like an a sub 0. That sub 0 just means initial. B is our growth or our decay factor. So here, every single time we've been doubling, it's been growing by a factor of 2 because we're multiplying by a factor of 2 every single time. Our exponent is a little bit different because it's not just x always. It could be x over some value, and that happens when we are doing it every so often. And so n would be the amount of time needed to grow or decay. So we're going to try to write a model for each one of these scenarios. If we started out with 4 pounds initially and it doubles every 3 hours, it's similar to what we just saw. We can have y equals, it starts out with 4, that's our initial amount, and it's doubling, so we'd be multiplying by 2 every single time. But it doesn't double every hour, it's every 3 hours. So I'd have to take that exponent and divide it by 3 because that's slowing it down. So if I represent what these would mean, x in this case is the number of hours, and y would be the amount of substance. Okay. In example 2, we have a substance that is 1.4 grams initially, and it triples every 3 days, not 3 days, 5 days. So y equals 1.4 there's our initial amount. We're tripling this time, so times 3 every 5 days, so x over 5. And these kind of hold the same way, where x is the number of days and y is the amount of our substance. Three is a little different because it's saying that we started out with 2.1 kilograms initially, and it has a half-life of 3,000 years. So when we talk about half-life, that's the amount of time it takes to decrease by a half. So another way to word this would be a substance is 2.1 kilograms initially and halves, not triples, not doubles, but halves every 3,000 years. So I'm going to write this as 2.1 initially, but it's not doubling, it's not tripling, it's halving. So it halves every x over 3,000, where x is our number of years and y is the amount of substance. We see half-life so often that we just kind of create its own formula. So it says y equals a times 1 over 2 to the t over n. A is that initial amount, t is the amount of time that has passed, but n is the half-life period. So it's always 1/2 because it's just half of the initial amount. Now we often represent that growth or decay as a percentage. So you've probably seen some questions like this before. And so if we started out with $500, but it grows by 3% every 6 months, it's not doubling and it's not tripling, but it's growing as a percentage rate. We can take that b value, what's going as the base of our exponential, and change it to 1 plus that rate or 1 minus that rate, because it's either growing or it's decaying. Think about if you just multiplied by 1, so I'm going to take that 500 and multiply by 1 every time. 1 to the first power, 1 to the second power, 1 to the third power, 1 to the fourth power. That is not doing anything, because when you just raise 1 to whatever power, it's going to stay 1. That's also saying you took 100% of that $500. But if it grows by 3%, and I do 1 plus my rate, which is 0.03, now it's gaining some percentage and it's going to grow. If we wanted to make it decay, we would subtract the rate from 1. And so this would show a rule as y equals 500 times 1 plus my rate, 0.03. 0.03 is the decimal form of a percentage. You just move that decimal back 2 places. If it's 3%, bring that back here. 3% becomes, the decimal is 3.0, back 2 spots is 0.03. And it's to the x over n. Well, we're doing every 6 months. If x is the number of months, then it's x over 6. So x would equal the number of months, and y would equal the amount of money. Example 2 says now we have a 5-pound substance and it's decaying by this percentage. Now we want to take that percentage and put it into a decimal. So I'd move the decimal back 2 and it would become 0.04275 when I put this into my rate. So y equals 5 is the initial amount times 1 minus, since it's decaying, 0.04275 to the x power. And I'm only doing to the x because it's saying it happens every year. I don't need to divide it by 1 because it's every single year. X still represents our number of years. Y represents the amount of substance that we have. So let's take these and put it into some real word problems and solve some things out. In example 3, we have the number of wolves in the wild in the northern section of Catawba County is decreasing at a rate of 3.5% per year. So there's going to be an important part of our problem. Your environmental studies class has counted 80 wolves in the area. Write an exponential function for this situation. So if I start it out and I have y equals, we start with 80 wolves. But we're decaying at a rate of 3.5%. So I'd be doing 1 minus 0.035. Take that percentage and put it into a decimal to the x. Since it's 3.5% per year, we can just do x. We don't have to divide it by 1. Now, after how many years will this population of wolves drop below 15 wolves? So we're looking to really solve this for when we're going to have 15 wolves. Well, x is representing our number of years, and y is representing the number of wolves. So that 15 is being plugged into y, and we're solving for x. So let's work this out. 15 equals 80 times, and we can do 1 minus 0.035 in our calculator. Comes out to be 0.965 to the x. And we just talked about how do we solve an exponential problem. So we're trying to get x by itself, but it's in the exponent. To solve an exponential, we need to isolate that part. So I need to get rid of 80 first. It's being multiplied, so we divide by 80 on both sides. And I have 0.965 to the x equals whatever 15 divided by 80 is. We can put that decimal, or you can put it into a fraction, so 3/16. But we're solving for x, which means I need to convert to a log. So I'm going to convert to a log and get log base. Well, the base is the base of the exponent. So 0.965 of 3/16 should equal x. We'll put that into our calculator, and then we'll have the amount of years. So if you remember, you have to press the log button 3 times, but our base is 0.965. Of is the inside, so I have of 3/16, which gives us a decimal, and we're going to have to round it off somewhere. So x is approximately 46.99 based off of this decimal. So really roughly 47, but what does that represent? 47 what? And x is the number of years. So it takes almost 47 years for the population to drop below 15 wolves. Okay. Example 4, we have the population of frogs in Old McDonald's farm is increasing at a rate of 83% per decade. So if I start out with 80 frogs yesterday, there's our initial amount. and we're increasing, so we're going to add our rate. So I have 1 plus my rate. 83% as a decimal is just 0.83, but it's not every X because it's saying per decade, which is 10 years, so it's increasing 83% every 10 years. So I'm going to make that X over 10, which now X represents our number of years, and Y would represent the population of the frog. So how many years, or how many frogs will be in the pond after 5 years? So now we know X this time. If I plug that in, I'd have 80 times 1 plus 0.83 to the 5 over 10. This time, everything is on the right. I don't actually have to solve anything. I can put this straight into my calculator. So Y equals, let's see, 80 times 1 plus 0.83, and then go to the 5 over 10 power. We get 108.22. So if we interpret what that means, so there would be approximately 108 frogs in 5 years. Example 5, now we have another decreasing. It's decreasing at a continuous rate of 1.3%. So 1.3% would be 0.013. The current population is 25,000. How many years is it going to take to decrease to 20,000? Let's start out with what we know. We initially have 25,000. It's decreasing. I have 1 minus 0.013 to the X. It doesn't say it's decreasing every 5 years, every 10 years, every so on. So we're making that every year. And then how many years is it going to take to decrease to 20,000? So I'm plugging in 20,000 because X equals the number of years, and Y represents the number of people or the population. So 20,000 equals 25,000 times, let's do 1 minus 0.013 to get 0.987 to the X. Because I'm trying to solve for X and it's in the exponential, we want to isolate the exponential. So we divide by 25,000. And 20,000 divided by 25,000 is 0.8 or 4/5, which is 0.987 to the X. To solve for an exponent, we convert to logarithmic form. So log base 0.987 of 4/5, or you could do your 0.8 there, equals X. Plug that into our calculator. Log base 0.987 of 4/5 is 17.05. So how many years will it take the population to decrease? About 17 years. It takes approximately 17 years for the population to decrease to 20,000 people.